The amenities, convenience, and comfort of the modern world are sustained by a constant supply of energy. However, our dependence on oil has resulted in catastrophic climate changes and vastly fluctuating gas prices. These consequences have intensified the need for a clean and renewable source of energy, particularly the unlimited solar power. Photovoltaics, or solar cells, are semiconductor devices that can directly convert solar energy to electricity. The most important characteristic of a solar cell is its power conversion efficiency. Increasing the power conversion efficiency of a solar cell can reduce the cost of electricity, making them competitive in today's markets. Conventional solar cells need an anti-reflection coating to reduce the reflection loss at the air semiconductor interface, which can be as high as 30 to 40% of the incident photon energy. However, the conventional anti-reflection coating is normally implemented with a thin dielectric layer, which only works for a limited spectral range at nearly normal angles of incidence. This could be a problem for the collection of solar radiation, which contains a broad spectrum and moves during the day. To work around this problem, scientists have taken inspiration from an unlikely source. It turns out that moth eyes are composed of well-aligned nanoscale structures that reflect very little light at night for the purpose of disguise. Therefore, light can pass through the structures easily due to optical diffraction, the so-called zeroth order grating. The diffraction results in nearly no reflection for a broad wavelength range and large angles of incidence. Such anti-reflective characteristics are exactly what is needed in solar cell applications. Mimicking the so-called moth-eye effect, researchers at the Green Photonics Laboratory of the National Jiao Tong University in Taiwan have developed a patterning and etching technique to fabricate very similar nanostructures on dielectrics. The biomimetic structures have a parabola shape with a period in the order of 500 nanometers. This is about 100 times smaller than the diameter of a human hair and are on the same scale as one photon wavelength. The solar cell with biomimetic antireflective structures exhibits a black color on the surface due to suppressed optical reflection for the entire visible wavelengths, in contrast to the blue color of the device with a conventional anti-reflection coating. The power conversion efficiency of these new moth-eye solar cells is superior to conventional cells, especially at oblique incidence of solar radiation. More importantly, perhaps, the innovative nanofabrication technique developed provides a scalable and cost-effective means of fabricating the improved solar cells in large volumes. So, thanks to the example of Mother Nature and some very creative thinking by some of the world's top scientists, we may be a step closer to reduced electricity costs and widespread usage of advanced solar power in the near future.